months ago. Okay. So he talked about the nuclear resonance techniques and applications in high pressure research. So today I'm just going to focus mostly on magnetic studies. I want to acknowledge the financial support from Compress, Argonne National Lab when I was working at APS, and recent support from UAB and NSF. Okay, so here is the outline of this talk. First, I want to give a very broad overview of several techniques routinely used for magnetic studies under high pressure, especially under static pressure in diamond cells. And then I'm going to give you a short introduction on the time domain synchrotron multiplier spectroscopy. And then I'll go into 3 examples on the applications in European-based iron pnictides, and then switch gear to dysprosium metal. So that's a different isotope, and how we can use the synchrotron multiplier to study the magnetism under high pressure. Okay, so here is it's a very general summary of the commonly used techniques for magnetic studies in diamond cell. So the first one is it's called the electrical resistivity, and so this experiment is commonly used to probe the change in transport properties from the magnetic order. And for example, here, this is a picture of the designer envelope fabricated in Yogeshwara's group. And this make the high pressure experiment, especially electrical resistivity experiment, extremely a lot easier than the traditional way of laying out these electrodes by hands, and that require a special skill with a high precision placement of the micron size electrodes. And this technique has been used up to 100 GPa, beyond 100 GPa. Here is an example of the studies of magnetism in dysprosium under pressure down in Jim's lab, up to 120 GPa. And another technique is the magnetic susceptibility technique. So that's a direct way of probing the magnetization in the material. So in this case, because the sample is typically very small, using the traditional coil placed outside the diamond cell, it's extremely difficult to probe the magnetic transition because the very small filling fraction. So in this picture here, this is again the designer envelope with the multi-loop coil deposit on the diamond culet to increase the filling fraction. So here, magnetic transitions in rare earth metals has been studied up to 15 GPa also. And then another group, Yejun Feng, at APS, back then he was working at APS and in Chicago, he came up with this special design. So with a compensation coil located outside is similar to the traditional coil, and then a secondary coil, which is located a lot closer to the sample. And in this case here, the filling factor is significantly improved. And with this setup, the rare earth magnetic transition has been measured up to several GPa. And of course, with the commercial squid, for example, here is a quantum design MP system, the squeeze system. You can actually put a non-magnetic diamond cell, small enough to fit into the ball, and you can actually measure the magnetic susceptibility under high pressure. And a recent work done by Mito et al. Just published in January this year, using a squid, commercial squid and small diamammu cell. And then another system is becoming more popular now. It's the XMCD. So the XMCD actually used the circular polarized X-ray by switching the left circular and the right circular X-ray, and we put the sample in the high magnetic field, and by take the difference of the absorption data, you can actually probe the magnetic state in the magnetic material. For example, here, this is the europium at L3 edge, and so europium in this case is a ferromagnetic order, and the XMCD is sensitive enough to pick up a antiferromagnetic order up to 20 GPa also. And another example is the nickel K edge. So nickel is a ferromagnetic system. And so people has done the XMCD up to 200 GPa, and to show the robustness of the nickel ferromagnetism. And of course, the neutron is also a very popular technique to study magnetism and also X-ray magnetic diffraction, although it's a pretty difficult, challenging to do under high pressure, but people have done X-ray magnetic diffraction up to 40 GPa. And this case here is an example of the resonant X-ray magnetic diffraction in lithium iridate. Okay, and so this is several techniques, all have advantage and drawbacks. So for example, the neutron experiment is great, but it's limited to fairly low pressure, maybe 40, 50 GPa. For example, in the case of europium 153, it's a strong neutron absorber, so you can't really study europium under high pressure. So that I'm gonna, next few slides, I'm gonna introduce briefly the Mossbauer spectroscopy and how we do high pressure studies at synchrotron beamline using a synchrotron X-ray. Okay, so this is just a busy slide to show the very basics, basic hyperfine parameters for the Mossbauer spectroscopy. So the Mossbauer effect is basically using a nucleus as so you are a nucleus. You actually look around the surrounding environment and then probe the electronic structure. So there are three types of basic, very fundamental hyperfine parameters. So the first one is called the Isomer Shift. So the Isomer Shift here. So this is the typical data you see in the conventional Mossbauer lab. So it's just a shift of the of this Lorentzian function in the absence of all the other hyperfine interactions. And so this Isomer Shift, the delta here, is actually a reflects the well, it's a direct probe of the S electron density at the nucleus, but it's also largely impacted by the other PDF orbitals, because there's a shielding effect and anti-shielding effect from other electronic shells. So the Isomer Shift here reflect the electronic structure of the mostly on the inner S electrons. And then in the case of quadruple splitting, so here, when you have quantum number of the nucleus larger than one half, and then you would have non-spherical nuclei. And in that case, in the presence of the electric field, you have quadruple splitting. And if you take a measurement in the energy domain, you will see a doublet. So this is typical for iron 57. So this example all limited to iron 57. For different isotopes, you would see very different transitions based on the ground state and the excited state of the quantum number for the nuclei. Okay, and then in the presence of external magnetic field, when there is a magnetic order from the electrons, or in some case on non-magnetic ions, if there is a transferred field from magnetic ions, and then you would expect to see a nuclear Zeeman splitting. So in this case, so this Hamiltonian here is proportional to the nuclear ball magneton and the internal field at the nucleus. And again, for iron 57, so in this case, these transitions would follow the dipole selection rule. And in the case of iron 57, you would see 6 transition lines. And in the energy domain, you would see very clear 6 absorption lines. Okay, and at the synchrotron beamline, how do we do this experiment? So let's go back just for 1 second. So here you see we need a source. Typically, it's called traditional gamma ray to excite the nucleus to the excited state. And this gamma ray in the traditional, the conventional lab MOSFET experiment, we typically use a radioactive isotope, radioactive source to excite the nuclei in the sample. So in this case here, we use a cobalt 57 and use that to excite the iron 57 and probe all these hyperfine interactions. So at a synchrotron beamline, we take advantage of this pulsed X-ray from APS. So typically we do experiment in the 24 bunch mode with the electrons coming in with a separation of 153 nanosecond. And then there's, we call it high heload monochromator to tune down the energy bandpath. And then after this high resolution mono, the energy resolution is further refined to 1 millieV also. And then we focus the beam onto the sample position, and we have placed a detector in the forward direction and collect the data. So that's pretty straightforward. And in this location here, we can put a cryostat, we can put a heater or a magnet, superconducting magnet, and do all kind of experiments under complicated sample environment. So of course, for different type of experiment, we use a different type of design for diamond cell. For example, this copper beryllium cells can be used for experiment in the superconducting magnet. Here, this is the 7 Tesla magnet we typically use in D station at sector 3 ID, because the available space there. And then several years ago, we developed this small diamond cell. That's this cell here that can go onto this cryostat with this special tubing going around this sample holder. We can cool this diamond cell to around 10 Kelvin. And here, this is a design by Stas. This big regular size membrane is used to change the pressure in situ at any temperature. And in one experiment, we also used, we did iron 57 measurement at low temperature. So this was done at 1690D, and we used a cryostat with a symmetric cell, and we used a double membrane. So we have one membrane mounted on the piston side and another membrane, second one, on the other side of the DAC, so we can change the pressure, stabilize the pressure at any temperatures. Okay, so here I just want to, this is a lot of data, but I just want to give you a flavor how unique is the Mossbar spectroscopy. So here, this first example is a bilayer system with iron and manganese fluoride. So here, this system was actually engineered so that the iron layer, majority of the iron layer is actually iron 56, which is not Mossbar active. And then this group here, they deposit a wedge shape of the iron 57. So this is very thin layer, about 10 angstrom. And then they apply an external magnetic field, and then with the X-ray almost parallel to the field, and they can actually determine this angle, the spin angle, at the different depths based on the iron 57. So with this setup, they can actually determine the spin rotation at, well, the depth dependence on the spin rotation. So this is a very, I thought this is very unique and very nice application. Okay. And then the second example, so here, just want to show this is actually an isotope selective, because the Mossbar effect, when you tune the energy to the nuclear resonant energy of iron 57, it's blind to iron 56. It only sees the iron 57, so it's actually isotope selective here, which is very unique. Not many techniques can do that. And then the second example here is a recent work done on the epsilon prime phase of the iron hydride. So from the synchrotron Mossbar experiment, by feeding the data, we actually resolved there are two iron sites shown in this crystal structure here. So there is a iron 1 and iron 2. So that's also very unique and difficult to be observed with other techniques. So here, this shows this technique is a local technique and is microscopic. You can actually see the detail sites based on the different hyperfine field resolved by feeding the data. Okay, and then another nice work is the NICO 69. So that has, NICO 69 has a nuclear resonant energy of 67 keV. And a few years ago, so this group at ESRF, they applied the pressure up to 260 GPa to study the magnetism in nickel. And that's not many techniques capable of magnetic studies under multi-megabar pressures. And then, of course, this a few years ago, I did the study of europium on the magnetism under pressure. So this data was taken at around 11 Kelvin, and we saw this collapse of magnetism above 84 GPa, and that coincided with the appearance of the superconductivity. Okay, and another interesting application is detecting the Meissner effect. So in this nice work on the hydride, sulfide, hydrogen sulfide, so they used a tin 119 foil. So this is fully enriched tin 119, and they put this foil immersed in the sulfur hydride. And when you cool down, actually there is a very low external field is applied. So that's less than 0.7 Tesla field. And they observe above the superconducting transition temperature, the external field can be seen by feeding this data. So that shows on the tin 119 sensor, there is a field which is similar to the external applied external field. But when you cool down to below the magnetic, the superconducting critical temperature, 59 Kelvin, and the external field is gone. All the external field on the tin 119. If you look at the data, it's basically linear decay, so there is no hyperfine field. So which means because the Meissner effect, the external field is expelled out of the tin probe. So this is a very nice way to observe, to detect the Meissner effect under multi-megabar pressures. Basically here, the limiting pressure is just the beam size. If you tune the beam size similar to the tin sample, tin probe there, you can go to several megabars. Okay, so in the periodic table, there are a few dozen of elements contains the Mossbauer active isotope. All has been observed in this elements shown in pink. So here in this talk, I will just focus on iron, a little on iron, because this iron is more commonly used, and then more on europium, and also a little on dysprosium, because these two are not very commonly used in magnetic studies. Okay, and then at APS, there are 5 isotopes. So iron, 157, and the krypton, and tin and europium dysprosium are routinely practiced at between sector 3, 16, and 30. Okay, just a very brief introduction on the Mossbauer effect in europium 151. So earlier I showed you the iron 57 case. So to compare the fundamental parameters for Mossbauer effect, so the europium 151 has a higher energy. For iron 57 is a 14.4. So with the diamond ammu cell, there is still attenuation at this energy with a 4 millimeter diamond height in the beam path. The absorption is more than, I think, 60%. And in the case of europium, it's 21 higher energy, so it's more favorable. And then the line width is about 10 times broader, and as a consequence, the half-life time is 10 times shorter. And the good thing about the europium 151 is the natural abundance is almost 48%, so which is very convenient. We don't need to artificially enrich the sample with iron europium 151, which is the case for a lot of the iron systems. But the transition here, you see, is fairly complicated. So if you actually make this energy splittings, and based on the dipole selection rule, you make a diagram of these transitions. In total, there are 18 possible transitions. And that makes the data analysis slightly complicated because there are just too many transitions. However, if you look at the lab Mossbauer data done with a radioactive source, you see there are not really 18 transitions. That's because many of the transition lines in energy, they are close to each other. And on top of that, there is broadening from the experiment setup of the radioactive source, and you actually see typically 8 transition lines. However, if you do a simulation in the time domain, which what we measure at the beamline at the APS, you see fairly complicated spectrum. But there is already a software package called Conus that's carefully can carefully, if you do it in a careful way or in the right way, then you can actually resolve the hyperfine parameters in europium. Okay, and europium it's a meat member of the rare earths, so it has very strong local magnetic moment. So for a 2+ europium, the 4F7 has a J equals to 7.5, and when you apply pressure, it's very easy to tune it to a 3+ state. In that case, you have J equals to 0, and it's typically a non-magnetic state, although there is an exception. And in energy, there's 2 states very close. So this valence state, whether 2+ or 3+, is very easy to be tuned by temperature, pressure, or even magnetic field. And the good thing is the isomer shift in europium 151 is very far apart for europium 2+ state and 3+. So this plot here is from Erjan Alp, and based on the data, published data in the Mossbauer data center database. So in the case of pressure, we can measure the isomer shift, and just based on this large separation, we can estimate the valence. So how do we do that? Keeping in mind, when we do experiment at the synchrotron beamline, especially at the APS, we actually take data in time domain. So in the time domain, we actually, if we just measure the sample itself, we lose the absolute energy scale in millimeter per second if you compare with the traditional Mossbauer experiment data. So here we actually place a reference sample with known isomer shift. For example, typically we use EUS as a 2+ standard, or EU203 or EUF3 as a 3+ standard. And in this case here, as an example, there is a EUS and EU203. We see this almost a periodic beating pattern, and that reflects this beating frequency. It actually reflects the energy separation in the traditional lab data. So by fitting this beating pattern, we can actually resolve the isomer shift on the sample. Okay, next I plan to give you 2 examples of application in europium systems. So the whole motivation is this rare earth-based iron pnictide superconductors. So we all know, I think most people know what is the iron pnictide superconductors. And so in this type of system, the iron actually contributes to the Cooper pair in the superconductivity. And when you introduce the rare earth ions into this system, it actually introduces a very strong local magnetic moment. So in this case here is a 1 to 2. So for example, it's the europium iron arsenic. So the europium would crystallize in a separate layer from this, physically separated from the iron arsenic layer. And then in another example, this is a different family, it's called 112. It has 1 europium and 1 iron and 2 arsenic per unit cell. And again, europium crystallized in a physically separated layer. And it's believed, based on the calculations, the iron, some of the d orbitals actually contribute to the superconductivity, and some other d orbitals contribute to this IKKY interactions, mediate the IKKY interaction on the europium. So with that, it contributes to a magnetic ordering in europium lattice, and also superconductivity in the iron arsenic layers. So this type of system, including another one called 1144, with the europium, rubidium, or cesium, and the iron arsenic layer. And a more recent group is the 12442, has more complicated structures. And all this different type of iron nictide families show this magnetism coexist with the superconductivity. Although here, in several of these systems, the magnetic order in the rare earth is not so clear because the resistivity doesn't show a very clear signature for the magnetic order. So this type of systems actually are a great playground to study the coexistence of the competition of these two phenomena. So I plan to just focus on the 112 and also give you another example, second example on a doped 122 system. So just to remind you, so in this system is so all the other type of systems, especially 122 and the 1144, they crystallize in a tetragonal structure, but the 112 actually is orthorhombic. And when you just look at the pairing compound with x equals to 0 here, it actually has two types of magnetic order. So one is a kink in the resistivity. The group making this sample actually speculate this could be from the magnetic order from the iron, because this located around 100 Kelvin, and in similar systems, iron magnetic order is on this scale. And then there, at lower temperature, there is another feature, and this group believe this could be from the europium magnetic order. And in fact, they also did Mossbar experiment in the lab to identify this feature here indeed is from the magnetic order in iron, and this is from the europium. And so in this system, the pairing compound is not superconducting, but if you just dope by 4% of nickel, it becomes a superconductor at lower temperature. So in this case here, there is coexistence of the magnetic order from europium and then superconductivity at lower temperature. But in the other systems, for example, 122 and 1144, the magnetic order temperature actually is lower than the superconducting temperature. So this is a very interesting and unique system to study the interplay of magnetism and superconductivity. So during the rest of the time, I will just focus on the magnetic study in europium. I'm not going to go into the superconductivity. So here, this is the typical data, Mossbar data in the pairing compound, the 112 system. So first of all, this is the europium data. Just to remind you, both europium and iron are magnetic ordered in this system. So with the Mossbar experiment, we can actually identify uniquely the magnetic order from europium and also iron separately. Okay, and so we did this experiment at the 3ID. We used helium pressure medium with this small miniature panoramic cell. We mount this cell in the helium flow cryostat and change the pressure at low temperatures. And by feeding this data points, so that's the scattered solid circles, we can actually resolve the magnetic hyperfine field and also the quadruple splitting if there is any. So here, this is just a plot of the hyperfine field at different temperatures and pressures. So you see this magnetic ordering temperature is fairly, roughly stable up to 5 GPa also, and at the higher temperature, the magnetism is suppressed, and when you go to 12.7 GPa, we didn't resolve any magnetic hyperfine field down to 15.6 Kelvin. And this dip here, this oscillation is coming from the thickness effect. And then we also measure the isomer shift by placing a europium, a standard, either europium 203 as a 3+ standard and US as a 2+ standard, because at higher pressure, we noticed this with increasing pressure, the isomer shift, so that's shown in this red curve here, is actually moving toward 0, toward the 3+ standard. And about 5 GPa, so this, for example, 12.7 GPa, the isomer shift is very close to 0. So if we keep using the 3+ standard, we wouldn't see much feature in the time domain data. So we switched it to 2+ standard. So this energy separation is larger, which gives more oscillation, faster frequencies in the time domain. Okay, and so again, so here we place this reference in the beam between the sample and the detector, and then collect the data. Typically, this if you notice, this temperature is higher than the magnetic ordering temperature, just to make the data or the data interpretation simpler. Because when you have the hyperfine field and quadruple splittings present, and the data can be very complicated. So on top of this, you add another beating pattern, and it's difficult to feed the data. Okay, and we also studied the magnetism in iron. And you see the data is more noisier because in this system, we used a natural sample. So the iron is not artificially enriched. So its natural abundance is only 2.1%. So that's why there's a low count rate. However, we were able to resolve the hyperfine field up to 8 GPa, down to 12 Kelvin, and higher pressure, like 10 GPa, we couldn't see any, couldn't resolve any hyperfine field. So here, this is the hyperfine field of iron as a function of temperature at different pressures. And so based on this information, the magnetic information from europium and the iron, we can construct the phase diagram in the pairing compound. So in the other types of iron nuclides, the 11122 or the 1144, there is tetragonal to a collapsed tetragonal phase transition at several GPAs. In the case of 1144, it's some of the system undergoes a half collapsed tetragonal and then a fully collapsed tetragonal transition. So we want to look at the crystal structure evolution under pressure in this orthorhombic crystal lattice. So we did X-ray diffraction at 13 BMC, and we indeed saw a change in the lattice parameters and above 10 GPa also. And by plotting the volume versus pressure, there is a discontinuity at the same pressure. So this happens above 10 GPa, and that's very close to the suppression of magnetism in both europium and iron. So we can't really, the critical pressure for europium and iron are really close. We can't really say for sure which the crystal structure is contributing to which magnetic transition. Okay, and so we also did measurement on this nickel-doped system. So this, with the 4% of nickel doping, this actually becomes a superconductor. So that's the red curve here. So the iron magnetism is completely suppressed. So we did also the europium 151 Mossbar experiment at high pressure and low temperature. And so we saw a collapse of magnetism at 7.5 GPa. So we didn't resolve any hyperfine field down to 14.7 Kelvin. And there is some impurity phase, a 3+ impurity phase. That's why you see this very fine, shallow oscillations. That's contributing to this oscillations, the europium 3+ impurity phase. And we also used a standard europium oxide 3+ standard to determine the isomer shift. So under pressure, we saw again the isomer shift is pushed toward 3+ state continuously under pressure. Okay, and to summarize the information we got from the Mossbar experiment. So this is the phase diagram of the pairing compound, including the iron magnetic phase. So that's shown in this blue color here, and also the europium phase, magnetic phase, that's shown in this orange color. And the around 8 GPa also, the magnetism from iron is completely suppressed. And then around 11 to 12 GPa, the europium is, the magnetism is collapsed. And in the case of nickel doping system, this phase boundary on the europium magnetism is pushed to lower pressure. And to summarize the isomer shift change under pressure, so we saw this continuously increase of isomer shift in both the pairing compound and the doped system. And if we just assuming the change of isomer shift is coming from the 4f electron change, so we just linearly extrapolate the valence, and then we expect to have almost a fully trivalent state above 15 GPa in both systems if we extrapolate the red curve for the nickel doped system to higher pressure. Okay, so next I want to briefly discuss another system. So this is the 122. So that's the ruthenium doped europium iron to arsenic 2. So in the pairing compound here, itself is the system is not a superconductor. So the superconductivity only shows up at between 2 and 2.5 GPa, depends on the pressure medium. But the superconductivity pressure boundary is very, very narrow. So it goes away at higher pressure. And by the way, this is crystallized in a tetragonal structure. So that's a different type of crystal lattice from the 112. And with 25% of ruthenium doping, the crystal lattice actually has a decrease in C-axis. So the C is compressed by this chemical pressure, decreased by about 3%. And because the ruthenium here is a 4D electron, so that's iron that's more extended than the 3D iron. So in this case, the IKKY interaction is expected to be enhanced on the europium side. So this system here, it shows a superconductivity around 23 Kelvin and a magnetic order from europium around 20 Kelvin. And they also did this group here, 2 groups, they did Mossbauer experiment to show identify the magnetic order from europium and iron. In the case of iron, the magnetism by doping, ruthenium doping, the magnetism actually is suppressed. So you add 5 Kelvin, you don't resolve the clear 6 transition lines. So here, only a peak broadening was observed. That could be attributed to the transferred field from europium to iron side. Okay, so again, here we did measurement on the sample at high pressure and low temperature, and we saw the magnetism is suppressed around 27 GPa down to 13.7 Kelvin. And we also put 3+ standard there to get the information on the isomer shift, and we saw a continuous increase of the isomer shift under pressure. And if we again naively think this isomer shift is attributing to the by the for F electron occupation, well, for F electron occupancy, in the case 3+ is for F6, right? And then 2+ is for F7. And if we assume the 3+ isomer shift is around 0, and then 2+ here, that's down here, minus 11.8. If we just do the linear extrapolation, then we can estimate the valence around 2.4 before 25 GPa. So that could be the reason the magnetism is suppressed at higher pressure. So, because we actually ran out of time when we were doing this Mossbauer experiment, so we didn't collect more data on the isomer shift at the higher pressure when the magnetism was suppressed. So we did another experiment, is a fluorescence yield X-ray absorption experiment at the europium L3 edge. So this was done at the 16 IDD. And we saw this, this is very beautiful data. We saw the continuous increase of the 3+. So this hump here corresponds to the europium 3+ transition, and this is the 2+. The lower energy peak is the 2+, and higher energy is the 3+. This separation in energy is around 8 eV. So that's very well resolved in energy. And we saw this continuous increase of the 3+ peak under pressure up to 38 GPa. And we wanted to get a quantitative estimate of the mean valence to compare with the measurement from the isomer shift. So we did a simulation, a model on the data. So the blue curve here, that's the data, and the red is the feet. So we modeled the experiment data with 2 octane functions to explain the jump for 2+ and the 3+, and then 2 Lorentzian functions to explain the peak for the 2+ and 3+. And then we took the ratio of the area under the 2 Lorentzian functions, and then estimate the valence based on the ratio of the area. And so here, this is the data extracted from the ZINs and isomer shift. So with the black square, that shows the estimated valence, mean valence from the europium, and from europium under pressure, and then the red circle, that's from the isomer shift, from the isomer shift data. And you see this continuously increasing, and the 2 actually agree with each other rather well. And so based on this estimation from the X-ray absorption data, and around 38 GPa, we see a europium valence above 2.7. And it's very almost fully transformed to 3+. Okay, if I plot the Curie temperature of the europium, and so that's shown in this blue symbol. And then I also have this valence estimated from the ZINs data and isomer shift data. So that's in triangle. And it seems there is correlations, or the critical pressure is around, based on the Mossbar data, is around 27 GPa also. And around this pressure, the valence is about 2.5. So that's pretty dramatic. And especially, so in this region here at the lower pressure, we actually saw an increase, continuous increase of the magnetic ordinary temperature. Even the mean valence of europium is actually going up. So here, what's going on, I think likely is the magnetic exchange interaction under pressure is enhanced. So that contributes to the increase of the magnetic ordinary temperature. And then later on, with the continuous increase of valence, and then the magnetic ordinary temperature decreases under higher pressure, and eventually completely suppressed around a mean valence of 2.5. Okay. How much time do I have?
You're muted, Steve.
I'm sorry. About how much more do you have, Wenli?
5 or 6 slides. I'll be quick.
Okay.
Yeah. Okay. So I will just switch gear and to show you very briefly the application of Dysprosium 161. So that's a different isotope, and this 151 has even higher energy than the europium 151. So that's 26.6 keV. And the natural abundance, again, is fairly convenient. It's almost 19%. And the half-life, half-life is about, this is the full lifetime, it's 41 nanoseconds, so that's longer than the European, but a lot shorter than iron. And again, the transition here, this is the ground state is 5/2, and the excited state is also 5/2, and the transition you see is again fairly complicated. So we have actually 16 transition lines in dysprosium, but that's actually not the most dramatic complication. So the complication comes experimentally, comes from the very large magnetic hyperfine field. So in this case, it's almost 600 Tesla at a low temperature. So this very large hyperfine field in energy domain, it would spread out up to 20 or 20 something centimeter per second. So if you estimate this energy separation in time domain, is actually give you only the inner lines would give you about 5 nanosecond features in the time domain. And then if you move to the next absorption line, that's actually sub-nanosecond. And our detector used in this type of experiment has a time resolution of about 1 nanosecond. So this is really limiting us to see the very fine features in the time domain. For example, here is a simulation of different detector time resolution. So the blue one is 10 picosecond, and green is 100 picosecond, and then the red one is actually the realistic time resolution with on the APD we used. So here, this is the example of the data actually using element array detector. So that has 180 picosecond time resolution. You see this very fine oscillations can be observed. Okay, so I'm gonna just flash the experiment data and the analysis. So this is the measurement at ambient pressure, 46 GPa and 141 GPa, and we saw the magnetic order up to 141 GPa and 230 Kelvin. So the problem with this experiment was we keep losing count rate whenever we approach the magnetic ordering temperature from low temperature. So we always do measurements during warming up from base temperature. And the reason we lost the count rate is all the data actually pushed to the earlier time. And if you look at the data, all the data I show, we start analysis of the data is actually useful from 15 to around 20 nanosecond. So anything before 15 nanosecond is we throw away because the bunch purity at the APS and the dead time on the electronics. So here, this is an example of the dysprosium synchrotron Mossbauer data taken at the ESIF, I think. And at above the magnetic ordering temperature, so this is on the spin ice dysprosium titanate, above the magnetic ordering temperature, the data is actually pushed to much earlier time because the isotope is short-lived, relatively short-lived, and we don't, if we are just start counting the data beyond 50 nanoseconds, we don't see anything. So that's the reason we actually had a difficulty of collecting data near the magnetic ordering temperature. But around 120 GPa, we actually saw something very interesting. We saw the magnetic hyperfine field persisted up to 280 Kelvin. And when the temperature was further increased to 300 Kelvin, this data was clearly not magnetic hyperfine field. So this is just a lousy feat with a quadruple splitting. I still trying to figure out what is going on in this data set, but it's one thing is certain is that there is no magnetic hyperfine field at 300 Kelvin in dysprosium at 120 GPa. So if I plot the hyperfine field at the different pressure temperature conditions, and so this figure here, this curve, that's the 120 GPa, and the magnetic ordinary temperature went increased to about room temperature, which is consistent with the measurement from Jim Schilling's lab. In dysprosium, the magnetic ordinary temperature indeed increased to close to room temperature. And we also saw at the higher pressure, based on our observation, if we think the loss of count rate is really close to the magnetic ordinary temperature, and then we can say that at higher pressure, the magnetic ordinary temperature is actually coming down. So around 120 Kelvin, it's almost the peak and the higher pressure. So if we extend this curve here, we would see something actually turn over and come down. So this actually fit into the Doniak scenario. So at high enough pressure, because the competition of the IKKY interaction and the Kondo effect, the magnetic ordinary temperature is first enhanced dramatically and then turn over at a higher pressure. With this J here, could be increasing pressure to tune this exchange interaction. So that's what we think is happening in dysprosium. Okay, with that, I would like to thank the collaborators for their contribution to this work. First of all, the nuclear rhythm scattering team at Sector 3, Erjan Alp, Jiyong Zhao, and Michael Hu, they taught me a lot about the Mossbar spectroscopy and the beamline instrumentation. And my graduate student at the UAB, Zachary Nix, he contributed to the European projects. And also I want to thank Yogeshwara for his generous support in many ways during the last 2 years. And also some of the X-ray diffraction data were taken at 13 BMC. Dongzhou Zhang was extremely helpful, and Sergey was also very helpful with pressure medium, the gas loading in many cells throughout all these experiments. And also I want to thank Daniel Haskell at the Sector 4, and Daniel was a great mentor in the last decade, and also contributed a lot in the dysprosium project. And we also did XMCD experiment on dysprosium, but because of the limited time, I didn't show the data. And also HPCAT, Yuming Xiao and Paul Chou, they were extremely helpful with the Zen's experiment. And of course, Jim Schilling, my PhD supervisor at WashU, and he introduced high pressure physics to me and trained me in different experiment techniques. And also Jing Song for his contribution in dysprosium project when he was in Jim's lab. And also I want to thank Guanghan Cao and Changqing Jin for their collaboration on providing the samples used in some of the European studies. Okay, with that, I want to thank you, and I'll be happy to take any questions and comments, suggestions.
Thank you very much, Wenli, for your detailed overview of the different projects you've been involved in. It's certainly a load of data to work with. You've done a remarkable job at trying to understand what's going on in these complicated systems. Are there any questions for Wenli? Please either unmute yourself or you can put your question in the chat box. Okay, so we do have one question. As you said, the bunch parity in the storage ring cuts off the beat patterns at short times for europium-151, for example. Is this expected to improve after the APS upgrade, or is this unknown?
I'm not exactly sure about the bunch purity. Is Urgent here? Michael? Maybe they can make a comment. No? Okay. Yeah, I don't know much about the bunch purity after upgrade. I do know the bunch separation is actually going to be shortened into half. So that will impact the iron experiment, especially the forward scattering or the synchrotron Mossbauer data collection. So previously we have this time window up to 153 nanosecond for data collection, but in future will be cut down to 74 nanosecond. So we lose a lot of information at a later time. But the europium dysprosium, because they are short-lived isotopes relatively, so the impact is smaller.
Okay, thank you. Ravi Kumar has a question. Ravi, do you want to unmute yourself and ask your question? Okay, well, I will ask the question. The europium valence change in the ruthenium doped system seems very similar to the high pressure
Yes.
resonant inelastic scattering studies published on the parent system. While comparing with the high pressure crystal structure, there is tetragonal to collapsed tetragonal transition around the pressure range where the valence changes. Did you see any such phase transition in the ruthenium doped system in the high pressure X-ray diffraction experiments?
We actually haven't done any XID on ruthenium system. So that's a future plan. And also, we are also interested in the superconducting behavior, how it changes with pressure, whether that's similar behavior with the 1144, with the suppression, continuous suppression of TC, the superconducting critical temperature, and also continuous enhancement of the magnetic ordering temperature. So here we want to also to measure the superconducting regime to see how this competing with each other or how we interact with each other. But it's interesting to see whether it's a similar tetragonal to collapsed tetragonal transition, but we haven't done that yet.
Okay, thank you. Following up on that, that europium iron arsenic system. So in the example you gave with the nickel doping, you're electron doping the system. Would you expect to see similar things, for example, if you hole doped it, say you doped with chromium instead, like the sort of cuprate superconductors would have sort of a symmetry about hole doping and electron doping. Would you expect to see the same thing here?
I'm not exactly sure whether chromium will go in there and actually you can, I'm not an expert in solid state synthesis, but I assume if it does go into the system and stabilize the structure, it's possible.
See, could I ask a question?
Of course.
Go ahead, Jim.
Okay. Well, you showed the dysprosium data where the ordering temperature went up very rapidly under pressure, and we thought that may have something to do with the Doniak phase diagram, that as you approach an instability, that for some reason the magnetic ordering temperature interaction strength gets bigger, which is sort of counterintuitive. And looking at your data on the europium iron ruthenium arsenic compound, there also you're seeing in a region where you're getting an increasing, you're approaching an instability, a valence change. You're seeing that the ordering temperature goes up by a factor of 3 or so, and then comes down. And it looks very similar to what you think is happening with dysprosium.
Well, in dysprosium, we didn't see any. Let me switch to that slide. I think maybe I forgot to mention the ZINS data. We didn't see any change in valence.
Yeah, but that's just a degree of the instability. I mean, the point is you're approaching an instability, and whether you're actually in the middle of it or not, that's another question. So I just wonder if maybe there's a similar physics going on in the two cases.
It's possible, but here it's clear at higher pressure there is a weakening of the magnetic moment. But in dysprosium is a different case. But I can't rule out this instability scenario in this case.
Daniel Haskell has a question. If a europium-3 compound is pressurized, is there an increase in isomer shift due to increasing S electron density at the nucleus under pressure?
I'm not exactly sure. It's possible because there is, if I go back to that plot of the isomer shift for different europium compounds here. There is actually a small variation for different compounds in different chemical environment. I'm not sure anyone has done that to compress a 3+ system and measure the isomer shift, but that would be interesting to see whether it's going up with pressure, with compression or not.
Yeah, I think we know at least for the case of europium oxide, when we compare Mossbauer and XAS, there seemed to be some sort of parasitic isomer shift increase in the Mossbauer and the pressure, and because of course the valence is also changing, it's complicated. So it will be really interesting to look at, say, europium 203 and the pressure with a reference sample, and see, for example, the valence of effective valence increases, but it's really a parasitic change and not a real valence change.
Yeah, I agree. Actually, John Say has done some recent calculations. We also did some experiment on iron, just iron metal under compression, and we observe a very large change in the isomer shift, like almost, I think, point. I can't say I don't remember the exact number, but the paper is coming out. There is a pretty decent change in the isomer shift on iron. So I expect to see also some change in europium.
Right, thank you.
Okay, are there any more questions for Wenli at this point? Well, if not, then please join me in thanking Wenli again for her really very interesting talk describing some really complicated physics. I'm sure it's a very fertile field for the future for lots and lots of students to get involved with you at UAB. So thank you for sharing your really elegant work with us today, Wenli.
Thank you.
Thanks,
Okay,
Wenli.
we'll see you next week, everyone.
Good to see you, Jim. Good to see you,
Good to
Steve.
see you.
Okay.
See you, Dan.
Hi, guys. Hi, Jim.
Bye now.
Take care.
Thanks, everyone.
Thanks.
Thanks, Wenli.
Thank you. Bye.